An autonomous vehicle emerges from a dark tunnel into blinding sunlight. The camera sensors white out, and the vehicle swerves sharply into the next lane. Despite the dangerous behavior, every hardware and software component in this car is functioning exactly according to its specifications. Traditional functional safety, or ISO 26262, solves for components that break. But this hazard is different. The system did not fail. It encountered an environmental limit it was never designed to handle. This is the domain of ISO 21448, SOTIF, the safety of the intended functionality. The early stages of the SOTIF standard are purely diagnostic. Clauses 5, 6, and 7 provide the tools to define specifications, identify hazards, and map the system's vulnerabilities against complex environmental triggers. However, analysis alone does not make a vehicle safe. To resolve these vulnerabilities, the engineering team must move into Clause 8. Clause 8 acts as the execution phase of the SOTIF process. It is the specific point where abstract risk analysis is converted into physical hardware and software modifications. This phase requires engineers to modify the system architecture, such as upgrading sensors, refining complex algorithms, or restricting operating parameters to ensure the vehicle can safely navigate unpredictable physics. Intended safety is not a theoretical exercise. It requires explicit, traceable engineering changes to the vehicle's design. The central engineering challenge is one of balance. Engineers must modify the system to eliminate a specific hazard without unintentionally compromising its core functionality. The standard provides two primary strategies to achieve this: avoidance and mitigation. Engineers must apply these strategies across 4 distinct implementation domains, ranging from hardware upgrades to the logic of the human-machine interface. Every modification applied directly changes the vehicle's operational design domain. If a risk is managed by restricting when and where the car can drive, the system's utility changes along with its safety profile. Clause 8 functions as an iterative calculus. It forces engineers to repeatedly weigh the safety benefit of a modification against its operational and technical cost. Clause 8 is not a constant state, but a conditional process. It is triggered only when unacceptable risk data enters the pipeline from 3 specific streams. The first path is through the initial design phase. This occurs when early hazard analysis identifies a severe residual risk, like sensor blindness at a tunnel exit, and routes the project back for physical modification before production begins. The second entry path is triggered during verification and validation, where the system is subjected to a rigorous simulation and physical testing. A trigger fires here if testing shows the system is failing to meet its safety targets, or if unknown hazardous scenarios are discovered during road trials. These discoveries mandate an immediate return to Clause 8. The final path is the release phase. This serves as a definitive failsafe. If the overall safety argument is found to be insufficient during final review, the release is blocked, and the system is sent back for further engineering. These entry triggers provide technical proof that the current architecture is unsafe, compelling the engineering team to intervene. To evaluate SOTF risk, engineers use a standard equation. Risk is the product of a hazard's severity and its controllability. On this matrix, the data points in the highlighted zone represent risks that are currently unacceptable. The first strategy is avoidance. The goal here is to drive either severity or controllability to absolute zero. If the hazard cannot physically occur, or if it has no impact, the risk is eliminated. When perfect avoidance is impossible or impractical, engineers turn to mitigation. This strategy focuses on shrinking the volume of risk, lowering the probability of an event, or reducing its impact until it falls below an acceptable threshold. Avoidance often involves a functional change. If a system cannot safely navigate a specific construction zone, the software is modified to force a driver handover before the zone begins. By removing the autonomous system from the scenario, the hazard is avoided. However, relying solely on avoidance can be counterproductive. If you avoid every complex scenario, the vehicle loses its ability to perform its intended function in the real world. This is where mitigation becomes essential. If a collision cannot be avoided through steering, the system may trigger automatic emergency braking. This doesn't prevent the obstacle from appearing, but it reduces the kinetic energy of the impact, mitigating a potential fatality into a minor incident. Mitigation provides the necessary defense in depth for when avoidance strategies reach their physical or operational limits. To execute these strategies, engineers utilize 4 specific categories of modification defined by the standard. Quadrant 1 is system modification. This involves direct technical upgrades, installing high-resolution 120 decibel cameras to handle extreme glare, or training algorithms on vast datasets of rare edge case scenarios to improve recognition. Quadrant 2 covers functional restrictions. If the technology has reached its limit, the operating envelope must shrink. This might mean disabling autonomous features during heavy rainfall or on roads without clear lane markings. Quadrant 3 is handing over authority. This focuses on the human-machine interface, ensuring that takeover requests are clear, multimodal, and provide the driver enough time to regain situational awareness. Quadrant 4 addresses reasonably foreseeable misuse. This uses driver monitoring systems to track eye movement and hand position, preventing a driver from over-relying on the system or becoming distracted. By combining these 4 vectors, engineers can cage unpredictable environmental risks without grounding the vehicle entirely. This node graph represents the complex interdependence of a modern vehicle. In such a system, Clause 8.3.6 warns that a modification designed to fix one hazard can inadvertently create a new secondary danger elsewhere. This tension is most obvious when tuning sensor sensitivity. If engineers increase sensitivity to ensure the car never misses a pedestrian, eliminating a false negative, the system may begin to identify shadows or steam as solid objects. This leads to phantom braking, a false positive, that risks a rear-end collision. Similarly, adding redundant sensors to improve perception increases the load on the vehicle's computer. This can lead to processor latency, meaning the car sees a hazard accurately but reacts too slowly to avoid it. Every modification must be cross-checked against the entire architecture. A local improvement cannot be allowed to degrade the safety of the global system. A Clause 8 modification is not the final step of the process. Instead, it triggers a mandatory update to the system's baseline specifications. This creates an iterative cycle. Engineers modify the design, update the official specs, reevaluate the risk, and return to physical testing. If the data still shows unacceptable risk, the cycle repeats. This loop only ends when 2 exit criteria are met. First, every known hazardous scenario must be mathematically reduced to an acceptable probability level. Second, engineers must probabilistically bound the unknown scenarios. Validation testing must prove that the chance of encountering an unpredicted fatal edge case is lower than the societal safety target. SOTIF engineering is a process of continuous refinement. It stops only when the mathematics prove the system is safe enough for public roads. The tangible result of this entire process is a document called the Specification of SOTIF Measures. This is more than a list of parts. It is a comprehensive engineering rationale that explains why each modification was chosen and how it contributes to the vehicle's safety. This document provides full traceability, linking the initial environmental trigger to the specific hardware or software change, and finally to the residual risk calculation. This specification is the technical bedrock of the project. It provides the evidence required for the final SOTF release argument in Clause 12. By following Clause 8, engineers transform the uncertainty of the physical world into a concrete, verifiable, and legally defensible engineering defense.